We've gotten the derivatives of e to the x and a to the x when a is any non-negative number not equal to 1. So now we take a look at the logs. So if we want the derivative of natural log of x, we're going to refer to what we know. We know the derivative of e to the x. So I'm going to rewrite this relationship as instead of y equals ln of x, in exponential form, that relationship can be expressed as e to the y is equal to x. And the reason I'm doing that is because I have a technique called implicit differentiation, which will allow me to find dy dx in this problem. So let's see, the derivative, again, remember we're trying to find dy dx. So the derivative of e to the y equals the derivative of x. Now the derivative of x is 1. The derivative of e to the y is e to the y times the derivative of the inside part, which is dy dx. So that means if I divide by e to the y, dy dx equals 1 over e to the y. But e to the y is just x. So it's 1 over x. So the derivative of natural log, the derivative of the natural log is equal to 1 over x. So I'm just going to make a comment right now about the graph of the function and its derivative. So here's a graph of ln of x. ln of x looks like this. So there's y, or let's say f of x equals ln of x. Now its derivative we just found was 1 over x. So the derivative is 1 over x. Now 1 over x has a graph that looks like this. It has that right arm. It also has this left arm. However, the left arm is really not at all relevant in this case, right? Because ln of x, remember, its derivative is going to tell us about slopes, right? So, like for instance, one thing you may notice is that the slopes of ln of x are always positive, and likewise, this right arm here is always positive, always above the x-axis. The other thing you may notice is that the slopes as you're closer to 0 for ln of x are really big, positive and really big. Well, the y values of 1 over x are positive and really big. And then the slopes decrease for ln of x as x goes to infinity, and that's what's happening for 1 over x as well. In fact, it looks like the slopes are approaching 0, and the tangent lines to ln of x are approaching 0 as well. But the point is that this left arm is not relevant because ln of x isn't defined to the left of 0 for x less than 0. So it said find the domain of f prime of x. Well, its domain would not really need this left arm, so its domain would just be 0 to infinity. All right, so that's just a minor comment. We'll see later, you'll see later when you do integrals, that we will eventually want to consider a left part of this graph here, but for now, this is just kind of a minor comment about the domain of the derivative. It should only really reflect information or give information about the slopes of the function that you're dealing with. So we've got the derivatives of a lot of different functions at this point. The very last one we need to look at is the derivative of log base a of x, where a is any positive number not equal to 1. So we're going to use the knowledge we've acquired so far, and we know the derivative of e to the x, a to the x, ln of x, and I think that's what I'm going to use. I'm going to use the fact that I know the derivative of ln of x, and I have something called the change of base formula, which is going to allow me to rewrite log base a of x as ln of x over ln of a. So if I view the function like that, then the derivative of log base a of x is the same as the derivative of ln of x over ln of a, which I think I'm going to write as, I'm going to write that 1 over ln of a is like a coefficient, so that it's obvious that that's just a number. And now the hard work's pretty much done. I know the derivative of this function here because 1 over ln of a is just a constant, and ln of x is a function whose derivative we just discovered in the last previously. So the derivative of ln of x is 1 over x, and 1 over ln of a is just a constant. So there's our derivative. You can write it as 1 over x times ln of a if you'd like. And there it is. There's the derivative. You may note too that when a is equal to e, that means that that the derivative, I'm going to actually write it like this, log base e of x, that's just the same as ln of x. According to this is 1 over x times ln of e, but ln of e is just 1. Right, so natural log is almost a very special case. Right, that's the same as ln of x. It's a very special case of this more general rule for the derivative of log functions. So alright, let's finish with this derivative here. The derivative of log base 3 of x squared, according to our rule here, we're taking the derivative of log base 3 of something, and according to our rule that's going to be 1 over that something times ln of the base. But we have to remember to times by the derivative of what's in that blue cloud there, which is 2x. And so we get, if we cancel, we end up getting 2 over x times ln of 3 as a final answer. Now another thing you could do is you could use a property of logs and move that 2 down. So log base 3 of x squared can be written as 2 log base 3 of x. And so then the derivative would be, this time the derivative would be, well remember that 2 is just a constant, so it's going to be 2 times the derivative of log base 3 of x, which is 1 over x times ln of 3. And you end up getting the same thing as you got here. Alright, so that finishes the derivatives of those logs and exponential functions. These are things that should be memorized. You can totally rederive them if you like these arguments, or you can follow these arguments. But they are, if you take AP Calculus, they're worth memorizing so that you don't have to waste so much time rederiving them.